All right, welcome everybody. Let's start into chapter 7. So atomic structure and periodicity, or specifically, we're going to be looking at electrons in an atom and then trends across the periodic table. Okay, so we'll just start by looking at electromagnetic radiation. So it's what it sounds like. It's going to be anything from light to it can also be expressed in terms of heat energy. Uh, but it is the propagation of electromagnetic energy. And if you look to the right here, you see this wave structure, and you can see one of the waves is the electric field, one of the waves is the magnetic field, and this is how they propagate. The electric field and the magnetic field are, well, let's just say, new term for you. They're orthogonal to one another. What you need to think of right now is that they're going to exist in this perpendicular field with each other. So they're propagating together and they work together, but they don't really have an overlap. And again, you can see that through this 90-degree turning of the waves from each other. Now, we want to understand some basic terms like wavelength. A wavelength is a distance between two identical parts of a wave, so like trough to trough, peak to peak. You can see a pretty good definition of wave function there. This symbol that you see for wave function might be new. That's the Greek letter lambda. Okay, let's see. We're also going to be working with frequency. Now, I'll show you what your book does. I'll show you what I do. Your book uses F for frequency, but I want you to learn it in a more traditional format, so I use the Greek letter nu. Okay, so I don't like the way that the program types that. It looks too much like a V. So a Greek letter nu. And so a frequency is how many waves per second pass a given point. Now, for a wave has to be a complete cycle. So let's think about that. One wave, if I start, oh, what would be good? If well, can't really see that. Where's my laser pointer? So if I start here, um, an entire wave, you'd go up through the peak, down, cross the zero line again, down through the trough, back up, and then in here. This whole cycle, that is one wave. And so then you ask how many of these complete cycles pass a single point in a given time. That's your frequency. So examples of electromagnetic radiation are ultraviolet rays, microwaves, infrared, radio waves. Uh, it's like a lot of times people don't think of things like radio waves as radiation or forms of light, but they are. So as this theory was being developed, what scientists found was that, and we're bringing back our proportional to mathematical symbol. So they found that wavelength lambda is proportional to 1 over the frequency. Now remember, we had another way of expressing this. So see, if wavelength was directly proportional to frequency, we'd have that. But we have proportional to 1 over frequency. The way you say that is lambda, so wavelength is inversely proportional to frequency. And so what they end up finding is that the wavelength multiplied by the frequency equals c. Well, I hope you know that c is going to be your speed of light. Now here, I put down your values for speed of light that you can use when you're calculating systems. And what I've done is your book shows you this value here, but it's going to be a lot easier when you're doing homework if we round that off to 3.0 times 10 to the eighth. So that's the value you're going to want to use when you're actually working through problems. But what this is showing you is that the higher your frequency, the shorter your wavelength. You're also going to see that that's going to correspond to a higher energy. So of course, we're all familiar with the visible spectrum of light. And so you can see the RGB spectrum, you can see across the rainbow of colors, but it's really this tiny little section of the electromagnetic spectrum. So you can see as wavelengths get shorter and shorter and shorter at this end. Can we see that well enough? What's a good color? Here. So down at this end, where your gamma rays are, you're getting very high energy, very, very short wavelengths, versus down at the radio wave end, you're getting very, very long wavelengths, uh, very small frequencies. So here, like radio waves can be on the order of 10 to the second meters. So maybe like one full radio wave could be around 100 meters, so versus these tiny, tiny, tiny little wavelengths down at the other end of the scale. But yeah, what you can actually see, this visible spectrum here is a very, very small portion of the actual light spectrum. Well, let's take a look at this equation that we had up here. Wavelength, lambda, times frequency, nu, equals the speed of light. And while we're doing this, keep in mind now you have a new set of units to look at. The units of frequency is called hertz. And so that unit is going to break down into inverse seconds. So the -1 exponent just means that seconds is in the denominator of a fraction. And you're used to this already because you've been using Avogadro's number, where Avogadro's number has units of moles. Okay, so hertz is going to be very similar to this, at least in formatting. Okay, so how did they come across that lambda times nu equals the speed of light or some kind of velocity? Well, let's start with a very basic physics definition. Speed, so speed or velocity, so v, is going to be delta r over delta t. In physics, r is a generalized direction. So it's a generalized distance. It's not necessarily an x, y, or z. It's just some direction. But what this is speed is distance over time. So then we have to ask ourselves, well, what is our distance? The distance that we're looking at in a wave is our wavelength lambda. And our delta t. So this big T here is called period. So period is our time for a wave. And we were talking about one complete cycle of a wave. So your period is how many seconds does it take for one complete cycle to pass a point in space? Okay, so if we now rewrite our speed, v is good, so delta r over time is going to be lambda over t. But we have a nice little definition here where our frequency, Greek letter nu, is going to be 1 over your period. And so if we look at this now, we can separate out your lambda over t is actually lambda times 1 over t. So the speed of your wave is going to be lambda times nu, but we know that this is an electromagnetic wave. And so if you think of an electromagnetic wave in a vacuum, so maybe in space, which is not a perfect vacuum, but it's a decent enough example. We know that this speed is actually going to be the speed of light. And so that's how they come up with it. And this is going to be for electromagnetic radiation in the vacuum that we talked about. So let's see, we have a radio station broadcasting at 99.5 megahertz. Calculate the wavelength of the corresponding radio waves. Okay, so what is this problem asking us for? Okay, what are some things we know? Our frequency, 99.5 megahertz, but we know that mega, the prefix mega is 10 to the 6th. So it's 99.5 times 10 to the 6th hertz. So another way we could write this, if we wanted to write hertz in SI units, and then of course C, 3.00 times 10 to the 8th meters per second. Okay, so we're looking for wavelength. We have our formula. C equals lambda nu. We want wavelength, so we need to divide through, and we're going to get lambda equals the speed of light divided by the frequency. So in this case, we're going to have 3.00 times 10 to the 8th meters per second divided by 99.5 times 10 to the 6th. And let's write inverse seconds as 1 over seconds so we can see how this crosses out our units. And what we end up with is 3.01 meters for your radio wave. So far the math isn't too bad. Let's start talking about the nature of matter. Well, early in the 20th century, scientists were studying something called blackbody radiation. According to classical physics, the intensity of a black body is something that can absorb and emit any frequency of energy. So it's kind of like a perfect thermal piece of material. And so what classical physics says is that the intensity of the radiation at high frequency should fly off to infinity. You get this spectrum of energy that just goes from zero all the way up to infinity. So that infinite energy at very short wavelengths was known as the ultraviolet catastrophe because it was a breakdown of the laws of physics. So the shorter and shorter the wavelength got, you got this impossibility of infinite energy. However, scientists were also measuring uh, the abundance. So what energy was the most, like the energies that were coming out of the black bodies, and they were showing that for individual temperatures, there was a spike that came up from zero, and most of the energy coming out was of a certain was a certain frequency, but then that number would fall off again back towards zero as you went out to further and further and further to smaller and smaller frequencies. So a good way to think of the ultraviolet catastrophe is imagine you're standing next to your stove and you have one of those heating coils. Well, as that heating coil got really, really hot, you would be getting hit with X-rays and gamma rays and a lot of really bad stuff, but we know that that doesn't happen. So the laws of classical physics were breaking down. So so what happened was a scientist named Planck came along and he made a new proposal. His proposal essentially broke down to that energy is quantized. So quantized energy means only specific energies and energy levels are available for the photons to be in. So the way he first started about that is you see here at the right, Planck's equation, E equals NH nu. Now, eventually we're going to get to the point where the N gets taken away, but as of right now, your allowed energy levels are going to be whole number multiples of H times nu. H is going to be Planck's constant. And he found that these high frequency packets, where classical physics predicted a spike to infinity for the number of those, he showed that they required massive amounts of very specific energies to exist. And for a given system, you just weren't hitting those kinds of energies, and that a distribution of energy packets or photons coming out of the system, very, very few of them, if any, were even hitting those energy levels. So the most common form of Planck's law here is E equals h nu. And so here you have h, Planck's constant, 6.626 times 10 to the negative fourth joules times seconds. So again, the whole point of Planck's law is that energy is quantized. In a system, you have very specific energy levels that are accessible, and then you're going to have a distribution of let's say your photons. Let's say the energy that your black body is irradiating. So what they were studying, they heated up these materials, and then they were studying the photons that were emitted by the materials. And so again, for any given temperature, a different distribution of photons were available, but they found that the energies were very specific, and the energy levels that could be reached were not actually going off to infinity. In fact, they fell to zero as you got lower and lower frequencies. But we want to be able to solve problems using this. So let's say we have a photon of ultraviolet radiation. So ultraviolet light UV possesses enough energy to mutate a strand of human DNA. What is the energy of a single UV photon and a mole of UV photons having a wavelength of 25 nanometers? Also keep in mind a photon is, did I write it down somewhere? Eh. A photon is essentially your particle of light. It's it's a gauge boson. It carries the electromagnetic force. So without photons, nothing would experience electric or magnetic force. It's just like it's a little packet of waves, but it's what light is made of. So let's see. What are we being asked for? What is the energy of a single UV photon? Okay, so how's 25 nanometers going to break down? That's going to be 25 times 10 to the negative ninth meters. Planck's constant. Remember, joule is your uh, unit of energy. Speed of light, meters per second. Let's see. So a single UV photon and a mole of UV photons. So we are going to end up needing Avogadro's number because your Planck's equation will give you the energy of a single photon. Okay. So a couple of things we're going to need. Well, we have Planck's law, Planck's equation, E equals h nu, but we don't actually have a frequency. We have a wavelength. So we remember that lambda times nu equals c. So our frequency is actually going to equal c divided by lambda. And so that means that our Planck's equation, or we can write it more as hc over lambda. And that's what we can plug numbers into to solve this problem. When you're working through problems like this, I want to see you do these little derivations. I had too much coffee today. I'm having to slow myself down to say the things that I need to say for the slides, but okay. So that means our energy, well, Planck's constant, 6.626 times 10 to the negative 34th joules times seconds. Speed of light, 3.00 times 10 to the 8th meters per second over your wavelength, which is 25 nanometers or 25 times 10 to the negative 9th meters. So your energy of one photon is 8.0 times 10 to the negative 18th joules. And I went ahead and you don't have to do this, but I think it helps. This is joules per photon. Okay, so there's one of your answers. Because this wanted also how much energy is in a mole of photons. Okay, well, so we remember from Avogadro's number that it's 6.022 times 10 to the 23rd something per mole. So in this case, photons per mole. So of course, photons cancels out, and we end up with 4.82 times 10 to the 6th joules per mole. So yeah, anything photons are the size of particles. So in ultraviolet radiation, you're getting about 4.82, so 4.82 megajoules per mole of photons. That's a lot of energy. I did put it in here. What is a photon? So we talked about light is actually a stream of these particles, a stream of these photons. Uh, I tried to come up with an image here to start getting across an idea for you. When we're dealing with quantum mechanics, we have what's called wave-particle duality. So that's why I said photons are like a packet of waves. The thing is electrons, neutrons, protons, they're all both particles and waves, and it kind of depends on the situation which which way you can actually view them. We'll talk about something called collapsing the wave function. If you take a measurement, well, then you kind of get a hard particle, but otherwise you're going to have waves. But you need to start wrapping your minds around this idea of wave particle duality. So it's like, is it a particle or is it a wave? Well, it's both. And so the photons, of course, are bosons that are the electromagnetic force carriers. In all of nature, there are force carriers. These fundamental bosons For example, you all experience gravity. Well, as far as we can tell right now, you wouldn't experience gravity if it was not for what's called the Higgs boson. And so you have these fields of bosons propagating through all of space-time, and you're being constantly bombarded. Like every molecule, every atom in your bodies, in every atom in matter, are being bombarded with these photon fields. And because you're being bombarded with them, that's why you're able to actually experience forces like being bombarded by the Higgs boson field. You're able to experience gravity. But even though light is a stream of particles, it still behaves like a wave. So it's a wave and it's a particle. So a good example of seeing the particle nature of light is by looking at something that happened in experimentation called the photoelectric effect. Okay, so again, try to come up with an idea. So when you have photons that hit what's called let's see, fundamental, do they call it fundamental? Oh, what was that frequency? Ah, threshold frequency. There you go. That's the word. Trying to get the proper terminology here. So we talk about frequency involving a certain level of energy. And so if you have photons that have a wavelength that allow you to hit a threshold frequency, when the photons hit a surface of metal, what will happen is you will actually get a stream of particles that come off that metal, a stream of electrons. And so that's the photo. So you hit metal with light, and all of a sudden you're getting an electric discharge, or you can get an electric current. So that wouldn't necessarily just happen with waves. You have to have some kind of energy transferred to the electrons to cause them to fly off their individual metal atoms. So you can start to think of light also as a particle. They come in, they smack the electrons, they transfer enough energy to the electrons for the electrons to escape and fly away. So as the intensity of light increases, that contain photons at or above this threshold frequency, the more photoelectrons you're going to get, and the more, so for example, the more current you could get. So a good way to think of intensity here is, so E is the energy of your photon, A is the surface area the photons are hitting, T is time in seconds, and then N is your number of photons. So you can see that the bigger N gets, the more intense your light beam is. And so also, the photoelectric effect begins right at this minimum energy where your E sub zero equals H nu sub zero. Nu sub zero is your threshold frequency that you need to free an electron from the constituent atoms. However, if you're only at just that frequency, the electrons will come off the atom, but they won't really move. They don't have enough energy transferred to them because it was all absorbed in pulling them off their atom. So once you start getting frequencies above that threshold frequency, then those photons are going to transfer kinetic energy to the electrons, and the electrons will start to move, or you're going to get a current. And so that's another factor of seeing light as a particle, because we can study collisions all day. We can study the collisions of in macroscopic situations and see kinetic energy transferred from one object to another. Well, these photons above the threshold frequency are actually transferring kinetic energy to the electrons and causing them to move once they escape. And that kinetic energy is really going to be governed by an energy difference. And so you think, well, what is the minimum energy needed for electrons to escape. Did I give myself room? Okay. And that's going to be your energy where your frequency is the threshold frequency or nu zero. And then how much energy is left over to transfer to the electron? Well, then you find out the energy at the frequency the photon is at, and you take a difference between the two. And so the velocity of a photoelectron, you can see here it's a square root of 2 times Planck's constant, where you have the frequency of your photon minus the threshold frequency over the mass of an electron. Let's see, how do we figure that out? It's a lot of things are going to become easier, especially in physics and chemistry, when you're able to actually do the mathematical modeling instead of just trying to memorize all these formulas. So let's look at this. So it's an energy difference. So what is the kinetic energy of a photoelectron? That is going to be a change in our delta energy based off our various frequencies. And so that's going to be the energy of the frequency of our photon minus the energy at the threshold frequency. And so based off Planck's equation, this is h nu, the frequency of our photon, minus h nu zero, nu sub zero, which is the energy at the threshold frequency. But then we say, well, what is kinetic energy? That's 1/2 the mass of your electron, v squared. Okay, so if your kinetic energy equals this energy difference uh, for photons at these various frequencies, we can say, well, that means we have 1/2 mass of an electron v squared is going to equal, I'm going to factor out Planck's constant, h nu minus nu sub zero. And now I'm just going to solve for v, the velocity of that electron. Okay, well, mass of your electron times v squared, multiply through by 2 is going to give you 2h nu minus nu zero. Okay, now v squared, 2h over the mass of your electron, and then you have to square root both sides. I don't like drawing square root symbols. And so you have the velocity of a photoelectron. We also find that under certain situations, photons can behave as if they have mass. So another aspect of being a particle. So it's actually a massless gauge boson moving at the speed of light in a vacuum, but uh, it can interact with inertia. It can increase or lose velocity. Well, let's be very careful there. When light travels through different mediums, the velocity can change. Your c is actually a cosmic speed limit. So let's not just start saying that photons can go above c. You get into all kinds of energetic weirdness if you work the math on that. But yeah, the velocity of a photon can change. And we know, for example, that there is a direct connection between energy and mass. I hope you're already kind of thinking about what that connection is. It's our very popular Einstein equation. So E equals mc squared. Energy is mass times the speed of light squared. We can rearrange that. Mass is going to be energy over c squared. Well, we have Planck's equation, so energy becomes h times nu over c squared. And then, of course, we remember that nu is c over lambda. We can plug that in there. So that's going to be h times c over c squared times lambda. The two of the c's are going to cancel out. And so we end up with mass is going to equal h c over lambda. So we can actually get a number for the mass of a photon, which is still, in essence, a massless gauge boson. So a lot of this stuff is very weird when you first start it, but you really start working on understanding this dual nature of matter. So you have both the particle and the wave nature. So another thing so we can reverse this by looking at de Broglie's theory, where it's like, well, can matter display wave-like properties? And yet, yes, it can. So, like for example, if you throw a baseball, it actually does have a wave function. You can calculate wavelength, all kinds of stuff. It's just that its wave properties are so tiny compared to its its mass and its size that it falls under classical physics. And so here again, you see this idea of protons, neutrons, particulate matter becoming waves, and it depends on the situation. They're going back and forth. Or here, if you look over on the right, you think of your atom, or you think of electrons orbiting around a nucleus. But instead of thinking of just like a solid electron, like a little ball just kind of orbiting around the nucleus, that electron actually starts to spread out into a wave function. And so you get, I guess you could call it like these electron waves uh, surrounding your nucleus. But yeah, here is your de Broglie wavelength that you can use to calculate the wavelength of any material, any piece of matter. So let's see, neutron diffraction is used in determining the structures of molecules. What is the de Broglie wavelength of a neutron moving at 1% the speed of light, which you're going to find is still really, really fast? Calculate the velocity of a neutron, the wavelength is 75 picometers. Okay, so part A, we're being asked for the de Broglie wavelength. Let's see, mass of a neutron, that is 1.675, 10 to the negative 27th kilograms. We know we're going to need Planck's constant. We're going to need the speed of light. All right. So we'll start with the de Broglie wavelength. H over mass times velocity. And we know that our velocity is 1% the speed of light. So that means, oh, didn't give myself a ton of room. Okay. So our velocity 1% c. So even 1% the speed of light is still 3.00 times 10 to the sixth meters per second, or you could say 3.0 megameters per second. It's still quite fast. So now we'll say that lambda is, so mass is the mass of your neutron. Kilograms. Let's see, velocity is your 3.00 times 10 to the 6th meters per second. And then my Planck's constant, joules times second. So lambda is going to end up being 1.32 10 to the negative 13th meters. Or you could also say 13.2 picometers. Now, we have to ask, did these units work out? Okay. This is just a little aside thing that I'm doing to analyze the system. So we have joules times seconds, because we ended up with units of meters over kilograms, meters per second. Well, you have to know that the joule is the Newton meter. That's going to cross out meters. Then this seconds is going to go up to the top because we've been working with that. So 1 over seconds goes up to the top. So this is going to be newtons times seconds squared over kilograms. Well, the Newton is the kilogram times meters per second squared. Then you have the seconds squared over kilograms. And seconds squared times 1 over second squared cancels, kilograms cancels. And I end up with meters. So yeah, the units do work out. But you have to know how joules breaks down. So again, the joule is Newton meter. The Newton kilogram meters per second squared times meters. So you could say that the joule is a kilogram meter squared per second squared. But however you can latch on to breaking these units down, make sure you're working on that. So then part B, let's see, calculate the velocity of a neutron with a wavelength of 75 picometers. Okay, so velocity. We have stuff up at the top we can use that'll help us. Our wavelength, though, is 75 times 10 to the negative 12th meters. Okay, well, we know that lambda is h over mv. We can rearrange that to get v equals h over m times lambda. Okay, so our mass, the mass of our neutron, 1.675 times 10 to the negative 27th kilograms, or lambda is 75 times 10 to the negative 12th meters. And h, our Planck's constant, 6.626 times 10 to the negative 34th joules times seconds. And we end up with a particle moving at 5.3 times 10 to the third meters per second. So about 5,300 meters per second. All right, atomic spectrum. You'll be doing a lab with this. You've also probably seen this before. So you know when light shines through a prism, you have all the different colors of the rainbow in there, and because of the way the prism works, the different wavelengths are diffracted at different angles. So that's why you see the rainbow form on the other side. And so we have a continuous spectrum, which is light through the prism, but we also have emission spectra. And these emission spectra are what we study for various elements. Uh, so we have emission and absorption spectra. So emission spectra, imagine light, let's see, light passing through is the absorption. So emission is you have a hot gas. When heat energy is in the system, the electrons in the gas, the atoms of the gas are excited, so they go up in energy levels. So when the gas cools down, those electrons fall from their high energy levels back down to lower energy levels, or which is called relaxation. The energy, the energy difference is emitted as a photon. And those photons are going to be emitted in very specific wavelengths. So an element will emit a very specific emission spectrum. Absorption spectra are going to be, you should get a pretty well identical spectrum. It's just this time you see you have your continuous spectrum with little lines taken out of it. Well, that's because you have your cool gas of some element and you shine light through it. And when those photons hit the element, electrons will absorb that light and jump from a lower energy level up to a higher energy level. And they can only do that with very specific photon energies. And that's again, so then those will be the black lines that you see where those photons were absorbed. And again, gives you a very specific spectrum for your element. So these spectra are like fingerprints for an element. So yeah, it's like here you see hydrogen. It will, if it's cool, it will only absorb very specific wavelengths. And if it's hot and cools off, it will only emit very specific wavelengths. So all of your elements are going to do this. And it all has to do with electrons either absorbing photons and jumping up to higher level energy levels, or relaxing from a higher energy level back down to a lower energy level and emitting photons. And we can actually start to calculate these energy differences by using our Planck's equation. So delta E equals hc over lambda, but you're going to see we're going to get another equation through through the Bohr model uh, that we can use to work in tandem with Planck theory to start to figure out what's going on inside of the atom. So here's the Bohr model. So Bohr talked about, he gave the idea of electrons moving around the nucleus of an atom in circular orbits. And so see here, kind of what we're talking about. You notice, imagine you have an electron here at a higher energy level, and it falls from your n equals 3 energy level down to your n equals 1 energy level. But when that happens and it goes from high energy to low energy, it's going to emit a photon here. And that kicks out that photon at h times nu. Keep in mind here, your core here is Z times E. Z is your atomic number, so number of protons. E is your base charge, so it's a measure of how much positive charge is in your nucleus. And then, of course, for the Bohr model to work and for electrons to not just fly off into space in a straight line, they have to undergo centripetal force holding them in their circular orbits around the nucleus. So one thing that Bohr found, was studying the angular momentum of electrons around a hydrogen atom, and again found very specific intervals of angular momentum energy. And so again, he's finding that these atoms are in fact quantized. Only specific energy levels are available. And he found that these energy levels are here, two different ways of expressing this. It's either negative 13.6 electron volts multiplied by z squared over n squared. Z is, of course, your atomic number. N is what's called your principal quantum number. And so again, here you see these as your n equals 1 is your lowest energy. Then you have your n equals 2 level, your n equals 3, 4, and 5. So the higher your value for n, the higher your energy. Another way you can write this equation, you have a conversion here of 1 electron volt is 1.6022 times 10 to the negative 19th joules. So you can also say that the energy is negative 2.178 times 10 to the negative 18th joules times z squared over n squared. Okay, so your book says at this point we're not going to derive this, I, however, am going to take you through this. Some of this is going to look very difficult and it's going to come at you pretty fast. But you need to think of mathematics as a language. You need to kind of get thrown into the neighborhood where the language is spoken and immerse yourself in it so that you can get used to it, because eventually you will make a breakthrough. Okay, so we talked about for the electrons to stay in circular orbits, they need to experience centripetal force. Otherwise, they just fly off into a straight path. Now, in physics, the definition of a centripetal force is mass times velocity squared divided by the radius of the circle. And this time, the mass is the mass of an electron. And this centripetal force that they experience is actually what we know as the Coulomb force. So that means the electric force that these electrons are experiencing, and that makes sense because you imagine the force they're experiencing is that electric attraction to the positive nucleus. Okay, so 4 pi epsilon z, 1 over 4 pi epsilon 0, that is your Coulomb constant. Then you're going to have z times e, which is your charge of your nucleus, multiplied by e, which is the charge of your electron, over r squared. Let's see. Epsilon 0 is called the permittivity of a vacuum. So it's how much electrical energy is allowed to flow through a vacuum, maybe outer space. And so it's a constant. You can look that up. Now, the centripetal force is the electric force. That's what's keeping the electrons moving in that circle. So then we can say, well, MEV squared over R is going to be ZE squared over 4 pi epsilon 0 R squared. Let's see, I'm going to multiply through by R. I'm going to get MEV squared ZE squared over 4 pi times epsilon 0 R. Now, we need another equation to work with. So again, Bohr found that these orbital angular momenta are quantized. So there's only specific ones available. So the term for angular momentum in quantum mechanics is L. And our definition, at least classically for angular momentum, is mass times velocity times your radius r. And Bohr found that these are quantized, and then the number is n times h bar. So again, n being some whole number multiple of this angular momentum energy, h bar, which is n, and the definition of h bar is h divided by 2 pi. So Planck's constant divided by 2 pi. They made a different constant because this Planck's constant divided by 2 pi showed up so much that they're like, well, let's just make that its own constant. Okay, so if we say that MEV times R equals NH over 2 pi, we can come up with a velocity of N times H over 2 pi ME times R. Now, we are going to take this and substitute it into here. Okay, so all right. Mass of your electron, your V squared, N times H over 2 pi mass of your electron times r squared. It's going to be z e squared over 4 pi epsilon 0 times r. We can go ahead and square that. So that's going to be n squared h squared. So you remember that that squared comes inside and it just hits every single term individually. 2 squared is 4, pi squared, me squared, r squared equals, let's see, e squared, which is, this is still our Coulombic force, the electrostatic force of attraction between an electron and a positive nucleus, 4 pi epsilon 0 r. You see that this mass and this mass are going to cancel out, at least one of those. So now you're going to have n squared h squared over 4 pi squared, mass of your electron, r squared. That is going to be z e squared over 4 pi epsilon 0 r. Okay, so I'm going to multiply through by 4 pi, and I'm going to flip this equation around to, well, you'll see why. So I'm going to move e squared over here, epsilon 0 r, because I'm multiplying everything by 4 pi. And so that's going to, so I'm going to still have n squared, h squared. On the bottom, the 4 is gone, and then 1 over 4 pi squared times 4 pi just leaves a pi in the denominator. Mass of your electron, r squared. And so then I'm going to multiply through by r squared. I'm going to move things around. I'm going to multiply through by r squared, so that's going to come over here. Your z e squared is going to divide through over here. Your epsilon 0 is going to multiply through up to here. I'm just not doing every step of the algebra. R squared over r equals epsilon 0 n squared h squared, and keep working with the algebra until you can do this. Pi mez e squared. And so the reason I did this, you see, is now I have this really nice equation that's very, very popular in quantum mechanics called the Bohr radius. Epsilon 0 n squared h squared. This is, what is the radius of the orbit at a specific energy level? Or how far away from the nucleus is your electron? Okay, so we have that. So we now want to try to get total energy of our system. So the first thing we say is, much more space do I have? Okay. So we know that our total energy is going to have to be a sum of the kinetic energy of our electrons in their orbit plus, and this is E sub V. And so in electricity and magnetism, V is the sign for electric potential. And I'm just going to tell you what this equation is because it is the it is the Coulomb potential. Okay, so we remember that kinetic energy is 1/2 mass of your electron V squared, velocity squared. And if you go back above, you remember that V squared is so 4 pi epsilon 0 R ME ZE squared. We did this above. Okay, so let's just work with this first for a second. Let's go ahead and substitute that in. Half mass of your electron. And keep in mind, your E is your fundamental charge. So that mass of your electron is going to cancel out. Kinetic energy of your electrons is d squared over 8 pi epsilon 0 rate and times the radius. And then your potential energy is your Coulomb potential. That's going to be a negative 1 over 4 pi epsilon 0 ZE squared over R. Okay, now, total energy. Kinetic energy plus potential. And then, so we're adding the potential energy, but since it's a negative, we'll put the negative sign in, and that's going to be ZE squared over 4 pi epsilon 0 R. Well, we can't exactly add these yet because we don't have the same denominator. So we're going to use a little trick. Remember, anything you do to one side of the equation, you have to do to the other side, except we're gonna play around with the idea of multiplying by 1. So you can imagine multiplying that by 1, that by 1, and that by 1. But the way I'm going to do it, my total energy, multiplying by 1 means leaving this the way it is, minus, I'm going to do 2 over 2. Now you might be able to see this and just correct your fractions to make sure to add them, but I'm just kind of showing you the process. Once again, Z is your atomic number, minus 2Z E squared over 8 pi epsilon 0 R. So see, what we were doing is getting the same denominator. And I keep saying epsilon 0. Maybe didn't really make that clear. So that's the permittivity of a vacuum, and that is your Greek letter epsilon. Again, it's a constant you can look up. It's essentially a Greek E. So now, when we subtract these two, the total energy of our system is going to be a negative ZE squared over 8 pi epsilon 0 R. Okay. However, we have a value for R. Let's scroll back up for a minute. We have our Bohr radius, and we can plug that in. Okay, this is going to be fun. Negative 8 pi epsilon 0. But our Bohr radius is epsilon 0 n squared h squared over pi mass of your electron CE squared. And then we get ZE squared on the top. Okay. So now let's multiply. We're going to take the stuff in the denominator and multiply it together. So when I have 8 pi epsilon 0, those pi's are going to cancel. Okay, so then what I'm going to get is a negative. So in my denominator, I'm going to have 8 epsilon 0, epsilon 0 squared, n squared h squared over mass of your electron, z e squared. In the numerator, I have z e squared. So now again, when you have a fraction inside of a fraction, like so you have that fraction in the denominator, it's going to flip, and then everything what's in this denominator is going to come up to the top and multiply. So remember your flip and multiply. This is going to equal negative me. Now we're going to get e squared times e squared is e to the fourth z squared over 8 epsilon 0 squared h squared n squared. And now you remember from our first equation for Bohr, we had a number times z squared over n squared. So we're just going to pull this apart. We're going to get a negative mass of an electron, e to the fourth over 8 epsilon 0 squared h squared times c squared over n squared. And the great thing is everything inside of that parentheses now is a constant. So you have your mass of an electron, your permittivity of a vacuum, and Planck's constant. Oh, and E is your fundamental charge. So you can look all those up, plug them in, and you're going to get a negative 13.6 electron volts Z squared over N squared. And that is a way that you can end up deriving the Bohr equation. So again, review this whole process. Like, learn to model systems mathematically. It's going to help you in the long run. All right, now that we've sufficiently scared you with some math, let's go on to some concepts. If we're thinking about the Bohr model, you're thinking about electrons orbiting around a nucleus, these various numbers for n, so n equals 1, 2, 3, 4, the higher the value of n, the higher the energy state. Your lowest energy state is n equals 1, that's your ground state. Let's see. Your ground state is actually, ground state is going to be a generalized term for your lowest energy state for all quantum systems. So you can have a molecule in a ground state. You can have, of course, different atoms in ground states, so on and so forth. Uh, when they were looking at the quantum mechanical model, they said that orbits are stationary states. So that means that your orbits are going to have fixed, defined energies. So again, we're getting back to this idea of quantization. You have these very specific states with very specific energy levels. If you look, you find that the energy of an electron in the state n equals 1 is more negative than the state n equals 6. So 6 would be a very excited, it would be an excited state. And so you find that these negative energies, and don't let that confuse you, these negative energies are what are called bound states. So you can think of these electrons inside of a potential well, inside of that electrostatic potential. And the negative numbers mean that electrons are still bound to the atom. They haven't escaped yet. So once you hit that E equals 0 level, that's where electrons start to escape. And they will then fly off the atom, and you'll end up with an ion. So of course, we know that we have our Planck equation, our delta E equals hc over lambda. But when Bohr was working with his model, he ended up finding that delta E, the energy between two individual states, is going to be your negative 2.178 times 10 to the negative 18th joules multiplied by 1 over n final squared minus 1 over n initial squared. Again, n is going to be that principal quantum number or the energy level you're at. So that one's actually easy to find because we remember that a delta is a final minus initial. And so we say, well, that's going to be negative 2.178 10 to the negative 18th joules. And then we're going to have c squared over n final squared. And then minus a minus 2.178 times 10 to the negative 18th joules. And then z squared over an initial squared. So again, in final and initial, I mean, you could be having an electron relaxation. So your final might be n equals 1, your initials n equals 5, or you're having excitation where your final is n equals 5 and your initial is n equals 2. It just depends. It's where you're at and where you're going to. And so we end up with our equation because for hydrogen, Z equals 1. Bohr was studying hydrogen. So I'm going to pull out the negative 2.178 and 10 to the negative 18th joules. And you get Z squared over N final squared minus C squared over N initial squared, or your negative 2.178 times 10 to the negative 18th joules. And you get, so 1 squared is 1. N final squared, 1 over N initial squared. And you might ask, like, are we going to use this for all atoms? And it's like, yeah, we technically are. It's an excellent approximation. And then it's like, you find out if you ever take a quantum chemistry that most of these scientists were studying the hydrogen atom because you had one proton, one electron, or physics calls it a two-body problem. Well, once you got beyond hydrogen, even to helium, you are now into the realm of the multi-body problem. So helium starts being a three-body problem, which, if any of you can actually solve the three-body problem, you'll be very famous. You'll win a Nobel Prize, win a lot of money, but it's just something that nobody's solved yet. So let's look at an exercise. Consider an electron for a hydrogen atom in an excited state. So that means it's at a higher level, higher value for n. The maximum wavelength of electromagnetic radiation that can completely remove the electron from hydrogen from that state is 1460 nanometers. What is the initial excited state for the electron? So how do you get from the state you're in to the electron being removed? Okay, this is going to bring in a concept of energy at infinity. So what is the state you were initially in? Okay, well, we're going to need H times 10 to the negative 34th joules times second. 1 nanometer is 10 to the negative 9th meters, and C is 3.0 times 10 to the 8th meters per second. Okay, so your electron starts in this level n, but your electron goes from n to infinity. And so really so any electrons that have escaped are said to be at an infinite distance. And all that means is they're no longer being affected by the positive charge in the core of the nucleus. So our delta E is going to be at that infinite state minus En. So we have two equations we need to work with here because let's see, we're looking for that value of N and we have a wavelength. So first off, we know delta E is hT over lambda. We also know delta E is a negative 2.178 times 10 to the negative 18th joules. One over n final squared minus 1 over n initial squared. Okay, so since these are both delta E, they're going to equal each other. We'll end up being able to solve for n using hc and lambda. Okay, so hc over lambda equals a negative 2.178 times 10 to the negative 18th joules. And our values of n, we don't know what n is, but we know our final state is 1 over infinity minus 1 over n squared, so we don't know what n is. Now, if any math professor saw this, they're cringing right about now. Okay, so I could put 1 over infinity squared, but infinity squared is just redundant. But you can't actually divide by infinity. It's not proper. But it gets to an idea that if you take calculus and you work on your limit theory, you know that as a function nears 1 over infinity, that it drops off to 0. And that makes sense. Any number divided by an infinitely large number is going to disappear. So that would you take calculus, learn your limit theory. It'll make more sense. It'll make the math professors happy. And I'm not just doing something mathematically improper. So now we're going to have hc over lambda equals, and so this negative 2.178 is going to multiply inside, oopsies, up to here, and that's a negative times a negative, so you're going to get a positive 2.178 10 to the negative 18th joules over n squared. And now we need to solve for n. Okay, n squared, hc over lambda, 2.178 10 to the negative 18th joules. Okay. N squared, if we divide by a fraction, we flip and multiply. You're going to give us 2.178 times 10 to the negative 18th times lambda over hc, and then in when we square root the whole thing. So now we plug in numbers. And what are our numbers going to be? So all right, so 2.178, 10 to the negative 18th joules. Okay, lambda is 1460 times 10 to the negative 9th meters over h is 6.626 times 10 to the negative 34th joules times seconds, and the speed of light is 3.002 times 10 to the 8th meters per second. And that whole thing is square rooted. And so your value for n comes out to be 3.9996, which we round to n equals 4. Your electron was at the n equals 4 excited state before it was hit with a photon and removed completely from the atom. Okay, so now we're going to end with a look at kind of the quantum mechanical model of the atom. Eventually, the Bohr model began to break down. It did okay at some descriptions, but it started to fail. Um, so in comes de Broglie had already showed that electrons have wave properties. So in comes some scientists like Schrodinger, who said, well, let's start modeling these electrons as waves. So he started looking at them as standing waves, which oscillate in time, but the peak amplitude profile does not move through space. What does that mean? So if you look here, I don't know, n equals 1, this wave is going to go up and down and up and down, but this peak and trough here is going to stay right where it's at. Same here. This is going to vibrate up and down, and you're going to get this seeming wave, but this is going to this peak will always remain here, and it's going to oscillate into the trough, back up to the peak, so on, and the same thing is going to happen over here. Same for all of them. That's what we mean by a standing wave. And so each one of these is a state with a total fixed energy. So then, of course, they started modeling these standing waves. So here you kind of see your Bohr model, your individual orbits around the central nucleus, but you can see these standing waves actually spacing out across these individual energy levels. So through his work, Schrodinger was able to come up with what's known as the Schrodinger Equation. So H hat psi equals E psi. I'm going to throw terminology at you, and we're not going to go into the quantum mechanical math, but I want you to start learning these vocabulary ideas. Psi is your wave function. So that is the mathematical expression that will actually map out your wave state. So what does your state look like? What is it? Uh, so psi is the expression for your quantum state. This expression, this Schrodinger equation is called an eigenvalue equation. And so eigenvalue is a German word meaning it's a value that defines the system itself. So what you have here is your hat over your H, that's called an operator. And so this is your Hamiltonian operator. And what you get is you get this mathematical expression that when I put it next to psi, it will actually do things to psi, like take a derivative or square psi, something like that. And the Hamiltonian operator will act on the wave function, and what comes out is a value that is a very specific energy. That very specific energy is your eigenvalue. It is a defining specific energy that belongs only to this quantum state. That's what we mean by eigenstate. So they started to find when these standing waves are positioned around an atom, they have to be, so the different energy levels have to be whole number multiples of the ground state energy. When you started to get energies, so values for n that are fractional, then the standing waves would not match up on the other side. And then you'd get these weird overlapping patterns, and it would just destroy the whole quantum state. So once again, you see that these quantum systems have to be very discrete whole number multiples of each other. They cannot be a continuous spectrum of energies. We get this idea that we start to get an idea that these electrons are actually waves that spread out around the nucleus, but they give us no, but the wave functions themselves actually give us no information. Well, they don't really tell us about the path the electron is following. This all ended up leading to what's known as the Heisenberg uncertainty principle, where you have delta x times delta mv, or mv is actually momentum, which we call p. So basically, your position multiplied by your momentum is it has an uncertainty in it, which it's either equal to or greater than Planck's constant divided by 4 pi, or 1/2 h bar. But basically, what this determined was you cannot know the position and the momentum of a particle simultaneously. You can't. You're always going to have an uncertainty. And so it's like, okay, well, if I don't know that, how do I exactly know where to find an electron? Okay, well, that's where we ended up in this thing called a probability distribution. So if I take my wave function psi and I square it, that is going to give me an equation that if I mapped that equation, it would give me a volume, it would give me an area where you're most likely to find, it gives you a probability of a exact point in space where you'd be likely to find your electron. So those probabilities are then, we start to get the shapes of our orbitals. So if you look here, on the left, you see s orbitals, on the right, you see a p orbital. And so you see these s orbitals end up making little spheres. So you have your 1s, which is a single sphere, your 2s, where you have your 1s here in the center, and a node of essentially zero electronic activity. And then you have another bigger sphere on the outside. So that's your 2s orbital, and then so on and so forth. You have your 1s in the center, your node, your 2s, and then a node, and then your 3s. And that's what all these little dots are. This is your probability distribution. It's like, where am I most likely to find an electron? Well, where these dots are more dense, that is the place where you're more likely to find your electron. Same with your p orbital, but see, they take very different shapes. And this would all make sense if you were at the point where we were doing the math and showing you the actual functions, and then you can map these functions as a region of space. But what you're doing is you're saying, well, this is where I'm most likely to find an electron in space. And so what your orbitals are actually enclosed spaces uh, that enclose 90% of at least 90% of the electron density for a specific quantum state. So it's like, okay, here's an enclosed volume, and most of the electron density is inside that enclosed volume. So that is more than likely where the actual electron will be. And so you notice, like, your 1s, your probability density has one huge spike, which represents your one sphere. And then how many picometers away from the nucleus that is. Your 2s has a lower spike and a bigger spike, where your lower spike is what's left in your 1s. Your bigger spike is your 2s shell, where you're most likely to find an electron at that energy. And then you have this, between the two peaks, you have a zero, which is your node, which is going to be basically a zero probability density of finding an electron. And then for your 3s, you see how you have your 1s sphere, your 2s sphere, and your 3s sphere. So you get 1, 2, 3 bumps. And your probability for finding an electron is much further out in your 3s energy bump. But this is how you start to look at orbitals. So are electrons actually moving in those shapes? Not really. They're more like electrons spreading out into wave patterns. Let's see, that looks like it's going to end today. Was there anything else that I wanted to say? Uh, this part of the chapter doesn't really have any math in it. You can kind of read through this quantum mechanical model to get an idea of where things were, where they went to. And I think the hardest thing to really wrap your mind around is this probability density, where you're most likely to find an electron. Because if you actually found the electron, you would perform what's called collapsing the wave function, meaning like, oh, look, there it is, it's right there. So then these orbitals and these wave patterns would completely disappear because you made a measurement. And so once you make a measurement, you found the particle. So now you're losing like most of, if not all of your wave properties, because now you have a particle. And I'm sure you're aware by now, quantum mechanics is very weird. But you need to read through this part of the chapter. You need to read through the whole chapter. Start getting your mind wrapped around this quantum mechanical system, because then tomorrow we're going to start into quantum numbers, which will actually help you define your electronic structure for your atoms and your elements. Uh, that's what we've been building to. We want to understand this electronic structure, and then we'll go into some trends that you can find across the periodic table. Alrighty. Talk to you later.